Yo, what's up everyone? Welcome to Equilibrium Part 5. Today we're going to go over acid-base titrations. So these tend to come up around like the end of the section. And so let's just do a bit of review on what it is. So remember, an acid-base titration curve is a graph that plots the progression of a titration as a relationship between the volume of titrant and the pH of the solution. So it's usually plotted on pH and the volume of your, in this case, since we're going to be titrating an acid, it's going to be the base, the volume of NaOH needed. So if we were to titrate a strong acid, something like hydrochloric acid, you would see that the pH at the start would be really, really low. And it would take this little S-shaped curve, and at like the middle-ish, you're going to have this really long vertical line. And that long vertical line is going to be really distinctive, and it's going to be present in basically all titration curves. If we look at something like a weaker acid, something like HCOOH, it would start at a higher pH and would still have that distinctive vertical line. Essentially, they have like the same shape, but their plot values are a bit different. And that the middle of where that vertical line is called the equivalence point. The equivalence point is the point at which all of the acid slash the base has been neutralized. And at the halfway point, so the half equivalence point, that's going to be the point at which half of the acid slash base has been neutralized. And there's an important relationship between the half equivalence point and the pH. And that's the pH at the equivalence point is going to equal the pKa of whatever you're titrating. So this is a really fast review, but let's move on to something known as polyprotic acids. So these are going to be acids capable of losing multiple protons. So a polyprotic acid might look something like this, where they have 3 hydrogens. And the way by which polyprotic acids work is that they dissociate one at a time. So at first, only one proton dissociates, and then the second proton dissociates, and the third proton dissociates. If we look at a real example of this, we can look at phosphoric acid. And you'll notice that as you progress on, the Ka values are going to change. You're going to have different Ka values for each dissociation. Oh, whoops, this one is wrong. But essentially, in every step, you decrease the Ka value. So the Ka value here, I think, had like a thing of like 10 to the negative 11th. Anyways, it's going to be smaller. It gets smaller and smaller. And if you look at the titration curve for this, it would look something like this. And you have 3 equivalence points, and you have 3 of these half equivalence points. And these half equivalence points represent the pKa value of each of these 3 steps here. From this titration curve, it's pretty obvious to see that a polyprotic acid does not dissociate completely in just one step. Instead, there are these 3 steps based on however many protons that you have. And so let's do a bit of practice with this. 1 gram of a weak base is titrated with 1 molar aqueous hydrochloric acid to give the data shown. What is the identity of the weak base? Essentially, the only information that we're given here is going to be in our answer choices, where we're given pKa value of these random bases. And so what is the pKa value of the base that is titrated here? The equivalence point is going to be right here, and you can see that it's at 60 mils of hydrochloric acid added. So the half equivalence point is going to be half of that, so at 30 mils of hydrochloric solution added. And so what is the pH at 30 mils? Well, it's going to be around here, which is like, 9.2, 9.3-ish. But remember, the pH at the half equivalence point is going to equal the pKa. And so our pKa here is going to be 9.3-ish. And the only answer choice that shows that is going to be ammonia, which tells us that our pKa value is going to be 9.3, which matches up with what we see in the titration curve. Let's do one more problem. So a 0.1 molar aqueous solution of H2SeO3 is titrated with 1 molar NaOH solution. At the point marked with the circle on the titration curve, which species represents at least 10% of the total selenium solution? Remember, this point right here is going to be our first equivalence point. And remember, the equivalence point is a point at which all the acids slash the base has been neutralized. And since since we're only dealing with the first equation here, the first equation being H2SeO3 dissociating into HSeO3 minus plus H plus, well, the fact that we're at the first equivalence point means that all the H plus and the base have been completely used up. So the H plus and this thing right here is going to be completely used up. And so the only thing that we're going to have left is going to be this little thing right here. And this little thing right here is going to be used in the second step, where SeO3 minus dissociates into H plus and SeO3 2 minus. And that's what we're going to see in this little part of the curve right here. And so really the only thing left at this point over here on the titration is going to be HSeO3 minus, which is answer choice C, and that is the right answer. Alright, that's all I have. I hope you learned something. This was meant to be like a quick little review with a bit more information, especially about the half equivalence point, because that really comes up a lot on the actual test. So I hope you learned something, and I hope to see you later for the final review. Thank you for watching.